chaplets. So the purpose of chaplets is to support cores. These are made of same material used for casting. So the chaplet becomes integral part of the casting. In addition to supporting cores, it also acts as directional solidification. So for example, direction solidification means cooling towards riser. That means the casting has to solidify first before the riser. And this one is core, which is made of sand. And these are called chaplets to support core. Empty space is, this one is empty space is casting cavity. You can use multiple cores, chaplets to support cores. So directional solidification is solidification towards riser, which we will discuss. Before providing chaplets to the casting cavity, it must be always thoroughly cleaned. So chaplets has to be cleaned to avoid the weak joining between the molten metal and chaplets. Chills. Chills are used for providing directional solidification. For providing directional solidification. Providing metallic piece at the junction of the L shape or any cross sections increases heat transfer. So that's why these chills are used for increasing the heat transfer. Suppose if it is L section, this is a casting, okay, and this area here you provide metallic piece. This is called chill, because area in this place is more, so to increase heat transfer. This is a mold, sand mold. So the purpose of chills is to increase the heat transfer, so which helps us to cooling very fast. Providing metallic piece at the cross sections or junctions, high cross section areas, the heat transfer will increase. So thermal conductivity of chill has to be high. So here we are directing the heat by adding additional chill. We are directing the heat to specified direction, heat in the specified direction. It is called directional solidification. Directional solidification. That metallic piece is called chill. It won't become integral part of the casting. Once you remove the casting from mold, you can remove the chill. You have to remove the chill also. So the chill material has maybe same as that one or different also, no problem. Example of materials is aluminum, aluminum is used majorly for low carbon steels. And another point you need to remember is melting point temperature is greater than the casting material. Melting point of chill is greater than the casting. Casting material or casting temperature means pouring temperature. Why? Because if the temperature of the chill is less, the melting point of chill is less than the pouring temperature or casting melting point of casting temperature, casting material temperature, then the chill will become liquid and it will melt and it will become integral part of the casting and it forms an alloy. So to avoid that, the melting point has to be more than the chill melting point has to be more than the casting. So another concept is padding. Padding is similar to chill and choplet. So here padding is like, for example, if you are doing ramming of a rectangular pattern, then the corners or sharp edges ramming won't be proper. So if you want to produce a sharp corner castings, the sand is not sufficiently rammed. To avoid that problem, we add some metallic element at the corners. So ramming at sharp corners won't be good enough to withstand molten metal flow. To avoid this problem, we add metallic pieces at the corners of the mold. It is called padding. So it's also used for directional solidification also. Next one, gating system. Gating system consists of sprue. So gating system means the molten metal we pour into the casting cavity, right? So how it has to flow. So the entire mechanism is called gating system. Gating system consists of one is pouring basin, two is sprue, three is runner, four is ingot. These are the major elements in the gating system. To understand this is this is the one simple casting. Casting cavity where molten metal will form casting. and this one is pouring basin. Here it is sprue. This one is runner. This part is ingot. And you may have heard of riser. This is riser, which stores molten metal, acts as reservoir. This is because it is not open to atmosphere. Blind, it is also called blind riser. So these are the major important parts. For purpose of pouring basin is to pour the molten metal into the pouring basin. It will come along the sprue and enter the runner. It will enter into the casting cavity through ingot. So once this cavity fills, it goes to the riser. So solidification starts from once the entire casting is solidified, then riser will solidify. So the riser has to solidify last. So solidification, actually here you need to first of all pouring or filling time. So pouring basin sprue has to be cylindrical and with reduced in area, conical shape with reduced in area of cross section. And runner is, you have to, it may be different shapes like trapezoidal or rectangular or V shape. It's like notches. Based on the notch, you want more coefficient of discharge, better go for trapezoidal runner. And ingot is the point where it enters into the casting cavity. The molten metal enters into the casting cavity. So that is about parts of the gating system. So here gating ratio, 2 marks gate bit, ratio of area of runner, sorry, area of sprue runner ingot, area of sprue is to area of runner is to area of ingot. In simple terms, it can be area of sprue is to area of runner is to area of ingot. So this is called gating ratio. So this area varies, there may be 4 to 1 or 1 to 1 to 1 to different areas. So whichever is minimum area, we have to take that area for calculation of filling time, solidification time. Anyway, we will discuss those points. So this they asked once in GATE 2010. In gating system, the ratio of 1:2:4 represents. So this ratio is standardized ratio. Whatever the numbers, don't worry about the numbers. The ratio, first area is sprue area and next is runner area and ingot area. That sprue area means area of the top sprue or bottom sprue. That you need to know first. So area of bottom sprue, area of sprue base, not on the top. Top is high area, right? Sprue base, you need to take less area. It helps us to know the discharge, how much is the maximum discharge. Okay, next is pouring or filling time. Pouring time or filling time. So it is a time required to fill the cavity is the minimum possible time. It has to be minimum. So time required to fill casting cavity T equal to volume of casting divided by area of casting into velocity. So area into velocity. So this is called volume flow rate. Area into velocity is volume flow rate. Is equal to A into V. That is equal to A max V minimum equal to A minimum V max. Anything you can take. So we take A minimum, which is equal to choke area, which is a minimum of area of sprue, area of runner, area of ingot. Whichever is minimum, we take that area, and maximum velocity root 2 GH, height of the sprue, depending upon the gating system. That anyway we will discuss that. So this is about pouring or filling time, how much time it will take to fill the casting cavity with the molten metal. And another point you need to remember is, so the flow of the molten metal in the gating system should always be laminar flow. The flow of molten metal should always be laminar flow. Okay, if it is turbulent, so the sand will come and into the integral part of the casting. It will cause defects again due to sand erosions. Next point is impurities must be separated from the molten metal. Impurities must be separated from molten metal in gating system. So before they enter into the casting cavity, before the molten metal enter into the casting cavity, impurities must be separated. Aspiration effect should be avoided. Aspiration is due to pressure difference. If aspiration effect is present, so air bubbles will go into the form into the casting, and it will form again, defective product will come. Aspiration effect to be eliminated as much as. So these are the points which we need to remember while designing the gating system. So there are different types of gating system. Types of gating system. Top gating. The ingot is provided at the topmost point of the casting cavity, is called top gating system. The ingot is provided at the topmost point of the casting cavity is called top gating system. Velocity at which the casting cavity is filling at maximum velocity, right? Because we are providing the ingot at the topmost point. So this is the storage of the molten metal. So this is example for top gating system. H is the height of the head, you can say. H, and molten metal will be present inside. So this one is casting cavity, sprue, pouring basin, it is runner, and the entry point is called ingot. Here velocity, pouring time or filling time of the casting cavity, T equal to volume of casting divided by A minimum into V maximum. So A minimum equal to A minimum of area of sprue, area of runner, area of ingot. V maximum equal to root 2 GH. Sand erosion takes place certain height of the casting cavity due to impact loads acting on the molten metal. So this top gating system is used only if the mold height, that cavity height, has to be less than 200 mm. If it is more than that, then because this molten metal falls from top height, so there is erosion takes place after certain height. It is used for small castings.